So, I6 is equal to root 2 by 3 V by omega OL into sin alpha minus sin omega OT plus I6 of alpha. Now, this expression is applicable in the first subinterval. Now, one has to note that alpha is the instant at which valve 3 is turned on. See, valve 3 is turned on at omega OT equal to alpha. Then what about valve 2? Valve 2 is turned on at omega OT equal to alpha minus 60. Then valve 1 is turned on at omega OT equal to alpha minus 120. Then if I take the previous valve that is turned on, that is before valve 1, the valve that is turned on is 6. So, valve 6 is turned on at omega OT equal to alpha minus 180 degrees. Now, what is the duration for which a valve conducts? Duration for which any valve, all valves conduct for the same duration. So, duration for which a valve conducts. So, duration is in angle. What is the duration? 120 degrees plus u. Okay. Now, when does valve 6 stop conducting? So, it is turned on at omega OT equal to alpha minus 180 degrees. So, valve 6 stops conducting, that means the current through the valve 6 goes to 0 at omega OT equal to alpha minus 180 plus, see, alpha minus 180 is the instant at which it is turned on. So, I have to add the duration for which it conducts. So, it is 120 degree plus u. So, this is nothing but alpha minus 60 degrees plus u. So, from alpha to alpha minus 60 plus u is taken as the first subinterval. That is the basis for taking this alpha minus 60 plus u as the end point of the first subinterval. Okay. So, what is happening to I6 at this instant alpha minus 60 plus u? 0. So, because valve 6 stops conducting. So, I6 at alpha minus 60 degree plus u is 0. So, I substitute this expression for I6 at this particular instant, which is 0, in the general expression for I6 that I have got. Okay. So, one should note that this is applicable for what values of omega OT? So, this is not a expression which is applicable always. This is applicable for omega OT greater than or equal to alpha and less than or equal to alpha plus u minus 60 degrees. So, it is of course applicable at alpha plus u minus 60 degrees. So, if I substitute this here, why I do this? I do this to get the expression for I6 of alpha. Say only after knowing I6 of alpha I have the solution for I6. Till then I do not have the solution for I6. Okay. So, if I do that, I get, so what I have to do is wherever there is omega OT, replace it by alpha plus u minus 60 and I6 is equal to 0. So, root 2 by 3 V by omega OL sin alpha minus sin alpha plus u minus 60 degrees plus I6 of alpha. So, this gives the expression for I6 of alpha. So, I6 of alpha is root 2 by 3 V by omega OL into sin alpha plus u minus 60 degrees minus sin alpha. So, substitute this expression for I6 of alpha in the expression for I6 that I have got earlier. So, again the same equation, substitute this here. So, from that I get I6 equal to root 2 by 3 V by omega OL. So, if I substitute this sin alpha which is there in the equation gets cancelled with the minus sin alpha in the expression for I6 of alpha. So, what I am left with is sin alpha plus u minus 60 degrees minus sin omega OT. Okay. So, let me call this as equation number 3. So, in the last class we got equations 1 and 2. So, this is 3. This is the expression for I6. Now, as we saw, there are two loop currents that are unknown. Say one loop current is already known, that is ID. The other two loop currents, I am referring to the circuit that was drawn in the last class. So, the other loop current is, of course, we can solve for any of the three quantities. So, we wrote the equations in terms of I6 and I1. So, we will solve for I1. So, I will not rewrite those equations 1 and 2. I will just try to use those equations and try to get an expression for I1. So, we had equation 1, I will just multiply it by equation 2 and subtract it from equation, no, I will multiply equation 1 by 2 and subtract it from equation 2. Okay. So, this is for getting the expression for I1. So, what do we get? 3L d I1 by dt is equal to EB, I presume you are having the equations with you, okay. EB minus EC minus 2 EB, 2 because I am multiplying equation 1 by 2 plus 2 EA. Is this okay? Or you want me to write equations 1 and 2? I have written, I mean I just don't want to repeat, okay. So, I presume you have those equations. So, this can be simplified. So, this is minus EB minus EC plus 2 EA and EA, EB, EC are balanced sinusoidal voltages. So, minus EB minus EC is equal to EA plus 2 EA, that is 3 EA. So, if I substitute the expression for EA, of course, one simplification that is directly possible is in this equation there is a 3 on both sides. So, L d I1 by dt is equal to EA. So, this means L d I1 by dt is equal to root 2 by 3 V sin omega OT plus 150 degrees. So, this has to be solved for I1. So, if I solve this for I1, I get root 2 by 3 V by omega OL into what? So, it is dependent on the instant at which the subinterval starts. Okay. So, it starts from alpha. So, what is the solution? Cos of See, either I can integrate and just find the constant of integration, or I can do a definite integral. See how I do definite integral? See, if I want to, so I can do both ways. I mean, both will give the same result. I do either I just say integrate this and take a constant of integration, find the constant of integration, or I can just take this. So if I di1 by dt is root 2 by 3 v by L sine omega ot plus 150 degrees. So if I employ the definite integral, it is nothing but integral of the right hand side, sorry, root 2 by 3 v by L sine omega ot plus 150, integrate with respect to time. Now integration with respect to time will be a bit difficult. So what I do is I will multiply and divide by omega o. So I will just multiply by omega o and divide by omega o. Is that okay? Omega o is a constant. So that I can put limits on angle instead of time. Okay. So what is the lower limit? Huh? Yeah, both are equivalent in fact. Now this is straightforward because you get the answer in one step, otherwise you get it in terms of constant of integration and then you find the constant of integration, again put back put it that in the equation. Now this is gives the answer in one shot. I think you are familiar, I presume you are familiar with this. See, you have to integrate from some lower limit, okay, and the upper limit is omega ot. I presume there is no cause of confusion. I mean, the dummy variable and the upper limit are one and the same, and I take the value of I1 at the lower limit. So what is the lower limit? It is, see, this expression is applicable from what instant? Yeah, from alpha. So, and this is alpha. So this gives the answer in one step. Otherwise you have to write it in terms of a constant of integration and then get the constant of integration again. So this gives I1 is equal to root 2 by 3 v by omega OL into, so integral of sine is minus cos, so I get cos alpha plus 150 degrees minus cos omega ot plus 150 degrees plus, what is I1 at alpha? ID. Now is this okay? See, what is the other way? Other way is you just do the integration with a constant of integration. I mean, both will give the same answer. I mean, okay. Now this is because I1 of alpha is ID. So let me call this equation number. I have used equations up to 3. So let me call this 4. This is equation 4. Now we have the expression for I1 and I6 in the first subinterval. Let us go to the second subinterval. So the equation 3 is the expression for I6 in the first subinterval, equation 3. Okay. Then equation 4 is the expression for I1 in the first subinterval. Now let us go to the second subinterval. So again we will draw the effective circuit diagram in the second subinterval. So by effective I mean showing only those elements that conduct current. Okay. Effective circuit diagram in the second subinterval. So the second subinterval actually starts at alpha plus u minus 60 degrees to alpha plus 60 degrees. So, which are the valves that conduct in the second subinterval? 1, 1, 3, 2. 1, 2 and 3 are conducting. Say in the first subinterval 6, 1, 2, 3 were conducting, 6 has stopped conducting at the end of first subinterval. So, the valves that conduct are 1, 2 and 3. So, if I just draw the effective circuit, of course, I have to show all the 3 sources EA, EB, EC. So, this is 1, this is 3 and this is 2. So, the cathodes of 1 and 3 are at the same potential. This is ID, this is VD. So, there is a current I1 which is flowing through valve 1, and the current through valve 3, which is I3, is nothing but for this subinterval it is ID minus I1. So, I am again employing Kirchhoff's voltage law, or in other words mesh analysis, to solve for the unknown current I1. One of the currents is already known. So, there are 2 loops, one loop current ID is known, the other current is I1. So, let us solve for I1 by employing Kirchhoff's voltage law. So, if I apply Kirchhoff's voltage law to this loop, I get L d by dt of ID minus I1 minus L d I1 by dt is equal to EB minus EA. ID is a constant, so derivative with respect to time of ID is 0. So, what I get is 2L d I1 by dt is equal to EA minus EB. So, 2L d I1 by dt is EA minus EB is the line voltage. So, what is the expression for EA minus EB? So, peak value is root 2V. So, EA has a phase angle of 150, EB has a phase angle of 30 degrees. So, EA minus EB is minus root 2V sin omega OT. So, it is L d I1 by dt root 2 L d I1 by dt is minus V sin omega OT. So, solve for I1. So, again if I try to directly use the definite integral, I get an expression for I1 as V by root 2 omega OL into what? Say if I take this I1, I have to integrate, after pushing this root 2L to the right hand side, I have to integrate with respect to omega OT after dividing by omega O, and the limits are, okay, if I let me write some more steps. Minus V by root 2L 1 by omega O integral of sin omega ot d omega ot. What are the limits? Alpha plus u minus 60 degrees. Upper limit is omega ot plus I1 at alpha plus u minus 60 degrees. So, from that we get the expression for I1 as V by root 2 omega O L. So, integral of minus sign is cos. So, I get cos omega ot minus cos alpha plus u minus 60 degrees plus I1 at alpha plus u minus 60 degrees. Now, this equation will be useful only if I know what is I1 at alpha plus u minus 60. So, how to get I1 at alpha plus u minus 60? Yeah. So, this is nothing but the value of I1 at the instant of starting of the second subinterval. See, second subinterval starts at alpha plus u minus 60. So, the value of I1 at this instant is same as the value of I1 at the instant of the ending of this first subinterval. Please note I1 is continuous. Why I1 is continuous? I1 is the current through the inductance. Now, please note I1 is the valve current, but is it also the current through the inductance? See, in this effective circuit it is, of course. Yeah, say these things can be used only if, say, value at the starting of the first second subinterval is equal to the value at the end of the first subinterval can be used as long as I1 is continuous. Is I1 continuous? Yeah, I1 is continuous. Why? Because the current through the inductance is IA. How is IA is continuous? Doesn't mean I1 has to be continuous. So, I mean, how do you say it is continuous? Any? Sorry? Yeah, so if you go back to the original circuit, so was it connected to in series with the same inductance? Okay. Can I relate two valve currents and the phase current IA? It is I1 minus I4. Now, what was I4 in the previous first subinterval? 0. Second subinterval? 0. So, for these two subintervals I4 is 0. So, therefore, IA is I1. So, I1 is the current to the valve. Okay. So, for IA is equal to I1 for alpha less than omega ot less than alpha plus 60 degrees. So, due to which I1 happens to be the current through the inductor, not always in this first interval which consists of two subintervals. Okay. So, I can use the previous equation. So, what is the previous equation? Previous equation is equation 4. So, this equation 4 is applicable up to alpha plus u minus 60. See, it is applicable in the first subinterval. See, please note this, let me repeat this. I6 expression given by equation 3 is applicable for omega ot greater than alpha and less than alpha plus u minus 60 degrees. And one can check that it is also applicable for omega ot equal to alpha and omega ot equal to alpha plus u minus 60. Similarly, the expression for I1 given by equation 4 is applicable for omega ot greater than or equal to alpha and less than or equal to alpha plus u minus 60 degrees. Okay. So, I use equation 4 which is applicable even for alpha plus u minus 60 degrees and get the expression for I1 plus alpha, I1 at alpha plus u minus 60 degrees. So, from 4 I1 plus I1 at alpha plus u minus 60 degrees is equal to. So, what you need to do is wherever there is omega ot, replace that by alpha plus u minus 60 degrees. So, what we get is root 2 by 3 v by omega OL cos alpha plus 150 degrees minus cos alpha plus u minus 60 degrees, that replaces omega ot, plus 150 plus ID. So, that gives I1 at alpha plus u minus 60 degrees as root 2 by 3 v by omega OL cos alpha plus 150. Cos alpha plus u plus 90 degrees can be written as sin alpha plus u, that is it, sin alpha plus u plus ID. So, this gives the expression for I1 at alpha plus u minus 60. So, I substitute this in the expression for I1 here. So, that gives me the expression for I1 in the second subinterval. So, I1 is v by root 2 omega OL cos omega OT minus cos alpha plus u minus 60 degrees plus root 2 by 3 v by omega OL cos alpha plus 150 degrees plus sin alpha plus u plus ID. Okay. So, let me give some number for this equation, equation number 5. So, this is equation 5. Okay. So, equation 5 is applicable from alpha plus u minus 60 degrees to alpha plus 60 degrees. Now, if I take the currents I1 and I6, say I have got the expression for I1 and I6 in the first subinterval, I got the expression for I1 in the second subinterval. Of course, in the second subinterval I6 is 0. Okay. So, can I relate I1 and I6? Say all the valve currents are identical except for a phase shift. So, if you take the two valve currents I1 and I6, they are identical except for a phase shift. So, what is the phase shift between I1 and I6? See, whatever happens to I1 would have happened to I6 60 degrees ago. Say at some instant valve 6 is turned on, means after 60 degrees valve 1 is turned on, after 60 degrees valve 2 is turned on. Okay. So, whatever happens to any valve, say I6, valve 6, The same thing happens to 1 after 60 degrees, same thing happens to 2 after another 60 degrees, and so on. Okay. So, if I take I6 of omega ot, it will be equal to I1 of omega ot plus 60 degrees, not minus, plus. Okay. So, I mean, is it plus or minus? I1 is lagging I6 by 60 degrees. So, it is plus. Okay, this is correct. Okay. Now, what I will do is, I will try to use the two equations which gives expression for I1 in the first subinterval and the second subinterval, and I will replace this in this equation omega ot by alpha. So, if I take I6 of alpha, it is equal to I1 of alpha plus 60 degrees. See, the first equation is applicable for any value of omega ot. Okay. So, I just put omega ot equal to alpha. Now, what I will do is, I will take the expression for I6 in the first subinterval. So, I have the expression for I6 in the first subinterval. So, it starts from alpha to alpha plus u minus 60. So, replace omega ot by alpha in the expression for I6 and take the expression for I1 in the second subinterval, which is applicable from alpha plus u minus 60 to alpha plus 60. See, what I am trying to do is, take the expression for I6 in the first subinterval. So, this is equation number. So, if you go back, we got the expression for I6 as equation number 3. This is equation 3. And replace omega ot by alpha. Then what I am saying is, this is equal to the expression for, take the expression for I1 in the, so I want to use this equation, I1 at alpha plus 60 is I6 of alpha. So, for that I have to take the expression for I1 in the second subinterval. So, the expression for I1 in the second subinterval is given by equation 5. So, this is equation 5, and replace omega ot by alpha plus 60 degrees. Okay. So, what does this give? So, let me do it. So, I will take the expression for I6 in the first subinterval and replace omega ot by alpha. So, wherever there is omega ot, I just put alpha. Okay. So, what I get is root 2 by 3 V by omega OL sin alpha plus u minus 60 degrees minus sin alpha. So, that is the expression for I6 in the first subinterval after replacing omega ot by alpha. So, this is equal to expression for I1, just now I got the expression for I1. So, this is equal to V by root 2 omega OL cos alpha plus 60 degrees minus cos alpha plus u minus 60 degrees plus root 2 by 3 V by omega OL cos alpha plus 150 degrees plus sin alpha plus u plus ID. Now, I will leave it to you to simplify this equation. Some trigonometric manipulations have to be done. So, it can be shown that ID, which is appearing as the last term on the right hand side, is equal to V by root 6 omega OL into cos alpha minus 30 degrees minus cos alpha plus u plus 30 degrees. So, this I am leaving it to you to derive. It is just simplification of the previous equation. Now, if you recall, we defined a quantity called short circuit current at the peak value of short circuit current IS. So, IS, the peak value of short circuit current, is root 2 V by 2 omega OL. So, I can write the expression for ID in terms of IS as ID is equal to IS by root 3. So, I just replace V by root 2 omega OL by IS, that is all. So, it is IS by root 3 cos alpha minus 30 degrees minus cos alpha plus u plus 30 degrees. So, this is the relationship between ID, IS, alpha and u in the case of 3 and 4 valve conduction mode. So, we got similarly a relationship between ID, IS, alpha and u for 2 and 3 valve conduction mode. This is applicable for 3 and 4 valve conduction mode.